Hello students, today we'll discuss about longitudinal wave. You know that transverse wave means what? Transverse wave is nothing but motion of the particle and propagation of the wave both are perpendicular to each other. In this case, longitudinal wave. In this case, medium particles are vibrating in this direction. And what about propagation of wave? Propagation of wave also in this direction. Both are parallel to each other. That wave is called longitudinal wave. For example, let's take one cylinder. In the cylinder, I'll fill with some gas. This one is frictionless piston. When you apply some force here, what happens? Whatever layers are contact with this piston now, that layers will get compressed. That layers will get compressed like that. Will get again. This one is called compression. Here also transfer of energy will takes place. You know that this basic how that transfer of energy will takes place. Finally, this compression will reach to another end. Here, rarefaction will form. These are rarefaction, and these are compression. We know that density is equal to mass by volume. In compression, at this point and this point, where compression are formed, at that point volume is what? Minimum. If volume is minimum, density is what? Maximum. And compression density is maximum. What about here pressure? Pressure also maximum. And in rarefaction, it is reverse case. At this point, volume will be more and density at this point will be less. And similarly, pressure at this point will be less, and pressure at compression is more. Okay. Velocity of longitudinal wave, it is depends on bulk modulus and density of the that medium. That is square root of bulk modulus and density of medium. You know that already in last chapter we discussed what is meant by bulk modulus, and it is a density of this medium, which gas we have taken here, that is medium, air or whatever maybe it is rho we have to take. According to Newton, he calculated the value of longitudinal wave. According to Newton, he said that, for example, the sound wave, longitudinal wave is nothing but sound wave moving from one point to another point here in air that is moving. According to Newton, at constant temperature, this medium, whatever medium you have taken, the medium temperature of this medium is constant. He said, at constant temperature, this disturbance or this energy is transferring from one point to another point. If temperature is constant, what about equation of an ideal gas? PV is equal to nRT. N is constant, R is constant, T is constant. PV is equal to constant. Okay. Which one is changing here? Here, which one is changing? Just now I said volume is changing and pressure also changes. Here, volume is more, pressure is less. Here, pressure is more, volume is minimum. In that case, pressure and volume both are varying here. That's why differentiate this with respect to pressure and volume. First term as it is differential of second term plus second term as it is differential of first term is equal to 0. Why? Because differential of constant is 0. Now PdV keep as it is equal to minus dP into V. Now P is equal to minus dP keep as it is divided by dP into V divided by dV, and P is equal to minus dP. This v can be written as, we can take this one from numerator to denominator. Of the denominator we can take dv by v. This p is equal to, this is nothing but what, bulk modulus, including negative sign. It is a bulk modulus. Why? Because negative sign indicates that decrease in volume. So already we know that here one object is immersed in a liquid. From all the side this fluid will exert a force. After exerting, the pressure is acting on this object. Due to that pressure, volume of that one, what happens here, decrease. In that case negative sign indicates that that decrease in volume. So including this negative sign, we know that that is nothing but bulk modulus. We know that velocity of longitudinal wave square root of bulk modulus divided by rho, density of that medium, and v is equal to square root of p upon rho. This one we got. Pressure in air, pressure of the medium is what, atmospheric pressure. We know that one. Let's calculate square root of atmospheric pressure is what, 1.013 into 10 to the power 5 upon 1.29. Density of air is 1.29. This velocity is equal to square root of 10.13 into 10 to the power 4 we can write. I'll shift this decimal point, one decimal point to the right, so we can write this one as what, 4, 1.29. After simplifying this one, we'll get 270 meter per second. Practically velocity of sound is not at 270 meter per second. Practically how much it is, 330 something will be there. So at 330 means it is not a correct value. Then whatever this Newton derived now, the velocity of sound calculated, this is wrong. Who said this one? This was wrong. Laplace. Laplace said that the velocity of sound is not at 270. It is different. According to Laplace, Newton said that this whatever energy will transfer from one point to another point at a constant temperature, he said, at constant temperature. But he said that, Laplace said that it is not at a constant temperature. So this whatever energy will transfer from one point to another point, this will transfer adiabatically. Adiabatically means energy will not transfer from system to surrounding, surrounding to system. See here, when here layers are there, compression we got. At the compression, temperature of this compression, what happens, increases. Temperature is not a constant, means that is not a isothermal process. According to him, this is isothermal process, he said. Why? Because after compression, temperature increased. Temperature increased within a fraction of second. This heat energy will not transfer to surrounding. Why? Because whatever surrounding is there, no, that surrounding is also air. Air is a bad conductor of heat actually. Okay, so that's why immediately that energy will not transfer to surrounding. The energy increase in temperature will be so as it is. That's why this, he said that the transfer of energy will take place adiabatically, he said. We know that adiabatic equation for fluid or gas, PV raised to gamma equal to what, constant. We know this one. Pressure is changing, volume changing, same, compression, rarefaction, compression, rarefaction, but adiabatically it takes place here. But in previous case, isothermally, according to Newton, here he said that when temperature of this compression increases within a fraction of second, that energy will transfer to surrounding, they'll maintain constant temperature, is said, but that is not actually correct. According to Laplace, energy transfer from one point to another point adiabatically, is it? You know that adiabatic equation, PV raised to gamma equal to constant. First term as it is, differentiate this one. Okay, differentiation of this one, gamma V raised to gamma minus 1 into dV plus V raised to gamma into dP is equal to 0. P gamma as it is, V raised to gamma, V raised to minus 1. We can split this one into two individual volumes, V raised to gamma, V raised to minus 1 into dV plus V raised to gamma into dP is equal to 0. Now take this. Okay, V raised to gamma is constant. Okay, take this term to RHS. P gamma, V raised to gamma, V raised to minus 1 into dV is equal to minus V raised to gamma into dP. V raised to gamma, V raised to gamma get cancelled. Just equate for P gamma. P gamma keep as it is. This one we can write dP upon V raised to minus 1 dV. P raised to gamma dP dV minus keep as it is minus keep as it is. This V raised to gamma can be written as a denominator. We can write now like this. This entire term is nothing but what? K, bulk modulus. In previous case, according to Newton, the bulk modulus is equal to pressure, atmospheric pressure. But according to Laplace, bulk modulus is equal to P into gamma. Gamma, you know that the ratio of Cp by Cv. We know that velocity of longitudinal wave or sound wave can be written as bulk modulus upon density. V is equal to square root of pressure into gamma upon rho. Just now we calculated this P by rho. How much you got? 270 into root gamma as it is. 270 we got now. Gamma is nothing but the Cp by Cv. The monatomic, diatomic, triatomic, the value of gamma is different. Here in air, in atmosphere, most of the air is what? Diatomic. That's why we can say that diatomic value, that is gamma, diatomic value is what? 1.41. After simplification, you'll get 330 meter per second. According to Laplace, whatever Laplace he calculated, the velocity of sound, he got a correct value. So that's why we will refer the velocity of sound, and to calculate velocity of sound, this formula only use. We should not use P by rho. P into gamma divided by rho only we have to use. Next, effect of pressure. Okay, on which factor velocity of sound is depends? On which factor velocity of sound is depends? First one, effect of pressure at constant temperature. Temperature is constant. What is the effect of pressure on speed of sound? We know that PV is equal to nRT. P is equal to what? nRT upon V. We know that velocity of sound is equal to square root of P gamma by rho. P gamma by rho. V is equal to square root of, substitute the value of P from this equation. P can be written as nRT upon V, volume it is, into gamma by rho. Gamma by rho. Next, velocity of sound is equal to square root of nRT upon V. Okay, volume can be written as, okay, volume keep as it is. We can replace this density or volume, anything. I'll replace density, gamma. Density can be written as mass by volume. Volume get cancelled. Velocity of sound is equal to nRT gamma by m. Gamma by m. So this nothing, m is nothing but molecular mass of that gas. Which gas? In which gas that the sound is propagating, that mass it is. Okay, velocity, number of moles constant, our gas constant, temperature also constant. We are talking about at constant temperature, temperature constant, and gamma also constant. Obviously that is diatomic. Most of the air contains diatomic gas, that's why it is also constant. And which one? Okay, we can say that effect of temperature. If temperature is not, both I'll say here only, both I will explain. So effect of pressure at constant temperature and effect of temperature, both I'll explain in this equation only. If temperature is not a constant, okay, if temperature is not constant, which one is constant here? N is constant, R is constant, gamma is constant, this one is constant. I have taken one gas. Okay, that gas, if you are taken on constant gas, M is constant, NR and gamma is constant, we can say that V directly proportional to temperature. When you have to use this one, effect of temperature. If temperature is changing, velocity of sound directly proportional to temperature if all are constant. What about effect of pressure? Effect of pressure, that okay, effect of pressure at constant temperature. Here we know that pressure is velocity of sound is equal to pressure gamma upon rho. This pressure is inversely proportional to volume, correct? Which one? Boyle's law. Pressure is inversely proportional to volume at constant temperature, we know this one. Okay, now pressure is inversely proportional to volume. What about volume can be written as what? Density into mass. Mass is constant, we can say that density is inversely proportional to volume also, we can say. Mass is constant here. Now compare these two. We can say that there is no change in velocity of sound. Why there is no change in velocity of sound? If, listen here, if volume increased, pressure decreases, correct? If volume increases, density decreases. This gamma value is constant. If pressure is decreased, density also decreases. See, compare these two. For example, initially this is 10 and it is 10. After changing the pressure, then if you change the pressure by 9, it is also 9. Why? Because if numerator changing, denominator also changes. According to these two equations, we can say clear. Volume increase means, for example, volume you are increasing, pressure decrease, and volume is increased, density also decreases. Numerator term also decreasing, denominator term also decreasing. The ratio will be what? Constant. When it is at constant temperature, effect of pressure is, so there is no effect of pressure on speed of sound. If temperature you are changing, in that case, effect of temperature is what? Velocity directly proportional to temperature, we can say. Now here, relation between velocity of sound wave is nothing but longitudinal wave and root mean square velocity. What is the relation? We know that longitudinal velocity equation, just now I derived square root of gamma RT by M. Yes, sir. See this one. For example, 1 mole I am talking, 1 mole. 1 mole if you are taken this one, gamma RT by M you can write now. Clear? Gamma RT by M. This one longitudinal wave. We know that RMS in case of kinetic theory of gases, we derived this one. 3 RT by M, correct? Both you divide. M get cancelled, RT get cancelled. We can say that V longitudinal divided by V RMS is equal to square root of gamma by 3. This is the relation between sound wave and root mean square velocity of that gas molecule. This one. Next, what is the effect of wind on speed of sound? If wind is blowing in this way, velocity of sound in this direction, it is making angle theta. We have to resolve this wind velocity, we can write W cos theta. Therefore, net velocity of sound can be written as Vs plus velocity of sound plus W cos theta. Will add up this one. Will add up. If wind is blowing in this direction, make an angle theta over here. This is Vs, this is wind, and this one is what? W cos theta. This is W sin theta. W sin theta, there is no effect on speed of sound. W sin theta. Why? Because this one and this component are perpendicular. Only effect will be what? W cos theta. Net speed of sound will be Vs minus W cos theta. W cos theta. So we can say that effect of wind also will count on speed of sound. Humidity. Humidity also depends on speed of sound, moisture and dry air. Okay, I'll take here first dry air. I'll take both. I'll take dry air. It is a container. You'll come to know the speed of sound increases or decreases in which air speed of sound is more, dry air or moisture. Moisture is nothing but wet air. Here container volume of this one and volume of second one both are same. For example, it is one, it is also one unit. Same volume I have taken. In this volume I'll take four molecules. Four molecules I'll take. Here also four molecules. Okay. Air. I am talking about air. Air contains what? Oxygen and N2. N2 and oxygen. Two oxygen molecule, two nitrogen molecule I'll take. And here also same oxygen 2 and nitrogen 2. Okay. Dry air is. Now second case. Hope you understood. So volume I am taking constant. In that volume, same number of molecules I have taken. Just for example, this is dry as it is. Now this one is what? Moisture. Moisture is nothing but a little bit wet air it is. Here two nitrogen molecules are as it is, and two oxygen molecules are as it is. Here one nitrogen as it is, one nitrogen is replaced with water molecule. Why? Because moisture contain what? Water molecule. And one more, it is water molecule. Water molecule. And similarly here also H2O, one oxygen as it is, one oxygen is replaced by one water molecule. Okay. Now calculate mass of this one. Mass. O2, we know that molecular mass of that one 32 into how many molecules are there? 2. And N2, mass number of N2 is what? 28 into 2 molecules are there, correct? This 2 into 2, 4, 6, 64 it is. And this one is what? 56. After simplification, both after adding 120 will get. Okay, simplify. Mass, total mass of this gas is what we got, or this air 120 we got. You calculate this one. O2, 32 only one molecule. N2 only 28 one molecule. And water molecule H2O, 18 into 2, 18 into 36, 36, what is 14, 15, 16. Okay, there's 3, 4, 5, 6, 7, 8, 9, 96. The moist air is what mass is? 96. And what about dry air? 120. Now density is equal to mass upon volume. Volume of these two containers you are changing? You are not changing. Volume is what it is? Constant. Okay, clear. Volume is constant. Though when mass only I am changing, I am talking about moisture and dry air. In moisture and dry air, what is the difference? Which one changes here? Mass it changes. Mass is changed here. And this is what it is. Mass here, moisture, mass decreased. Correct? Density also decreases. Velocity of sound is equal to square root of P into gamma by rho. In case of moisture, density of moisture less than dry air. Density decreased. It is atmospheric pressure will be there. Gamma will be, that is diatomic constant, and velocity increases. We can say that moist air. We can say that moist air is less dense than dry air. Dry air. Therefore, velocity is more in moist air. Moisture. We can say that humidity humidity directly proportional to velocity of sound. If you increase the humidity, velocity of the sound also increase. This is about humidity. Now we'll move to next concept, important, that is Doppler effect. Doppler effect, already all you know that what is meant by Doppler effect. Whenever there is a relative motion between source of sound and observer, in that case, whatever sound you are hearing, that sound is not actual sound, that is apparent sound. There is a change in frequency of sound. That phenomena is called as what? Doppler effect. If one person is moving towards source of sound, then frequency of sound, what happens here? Increases. There is a change in frequency of sound whenever there is a motion between observer and source. In that case, whatever change in frequencies, the apparent change in frequencies there, that phenomenon is called Doppler effect. Okay, we'll come to know, we'll discuss. Okay, for example, train is moving in this direction. You are standing at this point. Then speed of sound increases or decreases. So when the speed is moving towards you, the speed of sound increases. It means that whenever there is a motion, in that case frequency of sound, it is changing. Then actual frequency of sound is different. Whatever speed you are hearing, that is different. Okay, that's why. So whenever there is a relative motion between source and sound and observer, the apparent frequency of sound heard by observer is different from actual frequency. That phenomenon is called Doppler effect. Okay. When distance between source and observer decreasing, the frequency increases. The distance between observer and source increasing, frequencies decreases. So like that we can say. General expression for apparent frequency, that n dash, I'll take apparent frequency, is equal to, you remember this one general equation. If you remember this general equation, any numerical we can solve. V plus Vm minus V naught upon V plus Vm minus Vs into n. What is meant by n dash? N dash is nothing but apparent frequency. N is actual frequency. V, velocity of sound. Remember, V is nothing but velocity of sound. Vm, velocity of medium. Vo, velocity of observer. And Vs, velocity of source. Sign conventions are very important over here. Sign convention. First sign convention, first one. Direction of velocity of sound always taken from source to observer. Always from source to observer, we have to take velocity of sound direction. Always it is first rule. Second one, all velocities, whatever remember it is, velocity of medium, velocity of observer, or velocity of source. All velocities from source to observer are taken as positive. if you are measuring velocity of velocity of medium, velocity of observer, or velocity of source, if you are taking from source to observer, in that case we'll take a positive. And second one, all velocities from observer to source are taken as negative, are taken as negative. Observer to source, if you are taking any velocity, that is negative. Source to observer, if you are taking, that is positive. We'll come to know. I'll take one example over here. I'll come to know. If in this case medium is at rest, if medium is at rest, we can say that general equation n dash is equal to v minus v naught, v minus vs into n. Most of the numerical, they'll not give velocity of the medium. If they given velocity of the medium, in that case only you have to take. If they're not given, this general formula you remember. Observer will come in numerator and source velocity will come in a denominator. Just remember. So don't make any confusion. So if vs in numerator, vo in denominator, then that will be wrong. That's why velocity of observer in numerator, that will come. Okay, case 1. Source is moving, observer is at rest. Source, observer. Okay. First case, in this one, A, source moving towards stationary observer. This one is a source, observer is standing over here. Source is moving, source direction, velocity of source it is. And what about velocity of sound? Velocity of sound, obviously from where to where observer is going to hear that sound, then velocity of sound should be source to observer, this one v. Then velocity of observer is equal to what? 0. vs, we have to take positive or negative here? We have to take positive, because this velocity you are taking from source to observer. Source to observer, if you are taking, that one you have to take plus you have to take. We know that apparent frequency is equal to v minus v naught. Just I'll write this one in detail. So next cases I'll write direct only. V minus vs into n. This formula you know. Now apparent frequency is equal to v cap as it is. This is 0 upon v minus. If this minus you keep as it is. After that you have to apply sign convention, that is plus vs. Okay, plus vs. Don't write direct here only plus. Minus you keep as it is, after that plus, it is n. This n dash is equal to v upon v minus vs into n. This denominator term decreasing. If denominator term decreasing, this apparent frequency increases. Yes. When source is moving towards observer, whatever frequency or whatever sound heard by this observer will be more than actual frequency. Because denominator is decreasing, this term will increases. This is apparent frequency. Now, apparent wavelength, if frequency changing means wavelength also changes in some cases. Apparent wavelength, apparent wavelength, apparent wavelength, yes. Apparent wavelength lambda dash is equal to, wavelength is equal to what? Sound divided by frequency, correct? Wavelength is equal to velocity divided by frequency. We know this one, frequency. And lambda, wavelength, is equal to velocity of sound with respect to observer upon, why? Because apparent wavelength we are going to calculate with respect to observer, and apparent frequency. This apparent wavelength is equal to velocity of sound with respect to observer is what? V only. Observer is not moving, then we can say that only V only we can take, that V upon apparent frequency. What we got? V upon V minus Vs into n. This we get cancel. Apparent wavelength is equal to v minus vs upon n. Correct? V minus vn upon n. And also we can write this equal to v minus vs. N can be written as what? Actual wavelength. It is actual frequency. Actual frequency can be written as, see, this frequency cross multiplication. This cross multiplication, what we can write? V by lambda we can write. V by lambda. We can write this one V upon lambda. This lambda dash apparent frequency is equal to, as understood, this frequency, actual frequency is nothing but velocity divided by actual wavelength. Now V minus Vs upon V into lambda. Yes, lambda. Next, B case. B, source is moving away from observer. Here towards observer, now away from observer. Source and observer. Velocity of sound always will take source to observer, and source is moving away this side, Vs this side you are taking. It means that this direction from where to where? Observer to source. Correct? Observer to source. This direction I am talking, observer to source. If observer to source, this one will take as positive or negative. Negative will take negative. We know that this one on n dash is equal to v minus v naught upon v minus vs into n. This n dash v minus 0 upon v minus keep as it is, and this vs what you have to take here? Minus we have to take minus vs into n. N dash is equal to v upon v plus vs. Okay. Denominator term is increased. This will what happens? Decreases. When source of sound will move away from the observer, whatever sound heard by observer will be less than actual frequency. That's why this apparent frequency decreases when that source moves away from the observer. Now what we have to calculate? Apparent wavelength. Now apparent wavelength, we know that definition. Apparent wavelength is equal to velocity of sound with respect to observer, that is v. Apparent frequency v upon v plus vs into n direct. I'll write what you can write, n direct v upon lambda. This we get cancel. Lambda dash is equal to, correct? No, actual frequency can be written as v by lambda. We get cancel. We can write this term to numerator upon v into lambda. This is apparent wavelength. It is first case when observer is at rest. Next, second case. Second case, observer is moving, source is at rest. Okay, in that case, first, observer moving towards stationary source. Source, observer. Velocity of sound always from source to observer. Velocity of source is what? 0, because which is at rest. Observer is moving towards source, that VO. We have to take positive or negative. If direction of velocity from observer to source means we have to take negative. Already I said that sign convention. And we know that n dash is equal to V minus of minus V naught. Directly I am applying this one, minus of minus V naught, V minus 0 into N, correct? N dash is equal to V plus V naught upon V into N. Here frequency increases. Why? Because of V plus V naught. Now apparent wavelength. Apparent wavelength is nothing but lambda dash is equal to velocity of wave with respect to observer. Yes, velocity of the sound wave with respect to observer. Yes, velocity of the sound with respect to observer. What you have to take here? This is velocity of the sound. This is velocity of the observer. With respect to observer, velocity of sound, we have to take V plus V naught. Why? Because both are in opposite direction. Relative velocity I am talking here. If velocity of A with respect to velocity of B, both are moving in same direction, we will take VA minus VB. You remember that one. If both are moving in opposite direction, in that case, what will take? V plus VB. That's why these two are in opposite direction, V plus V naught upon apparent wavelength. Apparent wavelength is equal to velocity of the sound wave with respect to observer. I wrote this denominator N dash, we can write V plus V naught upon V into N. This one get cancelled. Lambda dash is equal to, we will come to numerator, and this n can be written as what? V by lambda. We get cancelled. Lambda dash is equal to lambda. In this case, what you can say? Apparent wavelength is equal to actual wavelength. In this case, there is no change in wavelength. And second case, observer is moving away from stationary source. Source which is at rest. Observer, velocity of sound from source to observer, velocity of source is 0, and observer is moving away from source. Velocity of observer, this velocity of observer direction from where to where? Source to observer. This one you have to take plus. Now n dash is equal to V minus into plus V naught upon V minus 0 into N. N dash is equal to V minus V naught. Why? Because minus to plus, minus upon V into N, which gives apparent frequency. What about apparent wavelength? Velocity of sound with respect to observer. Both are in same direction. Velocity of the observer with respect, velocity of sound with respect to observer. Both are in same direction. We can say here V minus V naught. Correct? Now apparent wavelength, frequency, V minus V naught upon V into N can be written as N, keep as it is. This get cancelled. Lambda dash is equal to, we will write numerator N can be written as V by lambda. We get cancelled. Lambda dash is equal to lambda. In both the cases, wavelength will not changes. Only there is a change in frequency. Okay. Now move to next case. Case 3, both are moving now. Case 3, source also moving, observer also moving. Observer and source both are moving. In this case number 3, again there are 4 sub cases are there. First case, source and observer moving towards each other. Both are moving towards each other. Here, source, observer. Velocity of sound, we know that source to observer. Velocity of source, velocity of observer. Yes. What you have to take here? Velocity of source. We have to take plus. Correct? Because source to observer plus you have to take direction. Observer. So observer velocity is from where to where, observer to source. That's why we have to take negative over here. We know that formula, apparent frequency is equal to V minus, and this one minus V naught will write, correct? Negative you have to take V minus this one plus Vs will write into N. N dash is equal to V plus V naught upon V minus Vs into N. This is apparent frequency. What about apparent wavelength? Apparent wavelength can be written as velocity of the sound with respect to observer. These two are in what? Opposite direction. Opposite direction means what you have to take? V plus V naught you have to take. What about apparent frequency? V plus V naught upon V minus Vs into N. This lambda dash, this get cancelled. V minus Vs divided by N can be written as what? V by lambda. Lambda will go to numerator. V minus Vs upon V into lambda. Yes, obviously here wavelength of sound will changes. Second case, source and observer moving away from each other. Source, observer, both are moving away. Velocity of source, velocity of observer. This one velocity of sound. Velocity of source is in which direction? Observer to source. This one you have to take a negative. Velocity of observer from where to where? Source to observer. This one you have to take a plus. Then standard formula you know, V minus into plus V naught you have to write. V minus you keep as it is. Vs what you have to take? Minus Vs into N. N dash is equal to V minus V naught upon V plus Vs into N. Yes, no? This is apparent frequency. Apparent wavelength. Velocity of sound with respect to observer. Both are in same direction. We have to take negative. V minus V naught. Apparent frequency we substitute over here. V minus V naught. V plus Vs. This N can be written as V by lambda. This get cancelled. Lambda dash is equal to lambda upon. Okay. Can you write like this? This one first Vs into lambda upon V. This is apparent wavelength. Correct? This is case 2. What about case 3 now? Case 3, in that sub case I'm talking. Case 3, source is moving behind observer. Yes, source is moving behind observer. Source, observer. Observer is front. Source is behind of observer. Velocity of source in this direction, velocity of observer in this direction. This is velocity of sound. Velocity of source we are taking from source to observer, we have to take plus. This one also plus we have to take. We know that apparent frequency is equal to V minus into plus V naught, correct? Because plus V minus plus Vs into N. N dash is equal to V plus into minus minus V naught upon V minus Vs into N. This is apparent frequency. Apparent wavelength can be written as velocity of sound with respect to observer. Both are in the same direction. Minus will take upon V minus V naught. Just you have to substitute this one apparent frequency. V minus Vs into N can be written as what? V by lambda. This one get cancelled. Lambda dash is equal to V minus Vs upon V into lambda. This is apparent wavelength. Fourth case, subcase, observer is moving behind source. Source, observer, velocity of sound this side v. Which one is front here? Source is front. Observer is behind of that source. Velocity observer and velocity of source both are in same direction from where to where? Observer to source. We have to take negative. Yes. Apparent frequency is equal to V minus into bracket. What you have to take? Minus V naught. V minus of minus Vs. Correct? Standard formula I am using. In that case, sign convention applying. N dash is equal to V minus of minus plus V naught V plus Vs into bracket N. This is apparent frequency. What about apparent wavelength? Velocity of sound with respect to observer, both are in this opposite direction. We have to take V plus V naught, V plus V naught, V plus Vs into bracket V minus lambda. Correct? This one, we know that lambda dash is nothing but velocity of sound with respect to observer divided by apparent frequency. This get cancelled. We can write lambda dash is equal to V plus Vs into bracket lambda upon V, which is equal to apparent wavelength. Apparent wavelength. Car is moving towards wall. Car is moving towards wall. Okay, it is another case here. Yes, this one is question I'll explain. Wall. Car is moving towards wall. Inside this car, one person is sitting. This whatever car horn is there, no? Car horn. That car horn is nothing but source now here. Car horn is nothing but source. We are going to calculate frequency of reflected wave. Question understood? This one is what? Incident wave, incident sound, and here sound will reflect back, and this sound is heard by this observer. This find frequency of reflected sound wave. Reflected sound wave we are going to calculate now. Okay, here first case and second case I'll take two cases here. Now this whatever car horn is there, no, initially car horn is a source. Car horn is a source, and this wall act as an observer. Okay, now this is velocity of sound, this is velocity of source. That velocity of source is nothing but velocity of car. Correct? Velocity of car. And velocity of observer is equal to what? 0. This wall is not moving. We are taking direction of velocity of car from source to observer. We have to take a plus here. Plus. Now here apparent frequency heard by this wall or observer. This observer n dash will take n dash. That n dash is equal to v minus 0 na. V minus of plus Vc, correct, into n. This n dash is equal to V upon V minus Vc upon into n. This is equation number 1 in first case we got. Clear? First case, the frequency heard by this observer. This wall act as a observer now. Now second case, now reflecting back, correct? This reflecting back, this wave reflecting back n dash, n dash. Now here car driver act as a source. Now here, sorry, car driver act as a observer. Now this will act as what? Source. See, initially this is acting as a source and this one observer. When sound wave incident, after incidenting, this will reflect. When this sound wave will reflect, no, in that case this source will act as this, whatever wall is there, no, wall will act as a source and this car will act as a observer. And this car is moving toward this side, that velocity of car which is equal to velocity of observer. Why? Because observer is sitting inside the car, we can take that Vc. What about velocity of the source is equal to 0? Velocity of the source is equal to 0. This one is source and observer. Now here whatever frequency will get, no, that frequency is nothing but n double dash. That n double dash is equal to V minus this velocity of observer is nothing but velocity of car. We have to take plus or minus here, minus we have to take. Why? Because the source is at this point. We are measuring this direction from where to where, observer to source. That's why it is negative. Minus Vc, correct, upon V minus 0, because source velocity is what? 0, into which one is the actual frequency for this case? For this case, n dash is the actual frequency, n double dash apparent frequency. In previous case, n is the actual frequency, n dash is apparent frequency. We got this one, n double dash is equal to V minus of minus plus Vc upon V into bracket n. Now dash. Now reflected wave, it is reflected wave. Now we can say that n double dash is equal to V plus Vc, keep as it is V. Now this n dash value I am substituting over here. Now this is V upon V minus Vc into n. This get cancel. N dash is equal to n double dash is equal to V plus Vc, V minus Vc. Yes, if they asked to calculate the frequency of reflected sound wave or frequency of the person who is sitting inside the car, how much frequency of sound he will hear, if they asked, we can calculate. We can use this formula, n double dash is equal to V plus Vc upon V minus Vc into n. This one, remember this equation in this wall and car numerical, we can use directly this formula. Okay. Next, bits numericals are very important. Bits theory, we know that one. Theory will not discuss. Bits only how to solve numericals I'll discuss now. Tuning for numerical only they'll give tuning for. First case and second case, two cases they will give. Waxing. Waxing is nothing but that is loading. And one more, that is filing. Okay. Here in that question, what they'll ask means loaded with. Then what is this filing? Filing or that is cutting also. Sometimes they will mention cutting. Okay. Here, in case of waxing or loading, frequency of tuning fork what happens? And in case of filing, the frequency of tuning fork what happens? Waxing means we are adding some mass. Loading, we are adding some mass. Mass you are increasing. If mass you are increasing, the frequency changes. As the frequency changes, the frequency increases or decreases. The frequency decreases. Frequency decreases. Frequency decreases. Why? Because we are adding some mass. Mass you are increasing, then frequency decreases. Frequency decreases. Here filing, you are removing some portion from that tuning fork. In that case, frequency decreases. Here frequency increases. Okay, remember these two cases. I'll solve that some numerical. Tuning fork, one tuning fork is there here. Two tuning fork I'll take. Two tuning fork. One is unknown frequency. Unknown. What is the use of that bits? To calculate unknown frequency, we'll use this bit phenomena. This tuning fork A, tuning fork B. Frequency of tuning fork A is 256. This one is the frequency of B, it is unknown. We don't know this one, we are going to calculate. When this tuning fork and this tuning fork, when sounded together, how many bits are forming means here bit frequency 4 bits per second, 4 bits per second. Then calculate unknown frequency. Okay, after waxing, here one of these two tuning fork is loaded. For example, this one is loaded. This one is loaded. If tuning fork A is loaded, after that, after loading, they may mention frequency, bit frequency increased. They mention increased, bit frequency increased. Okay, once again I'll explain question. Here there are two tuning forks, tuning fork A and B. Frequency of A is 256, frequency of B we don't know. When initially sounded together, how many bits are forming? 4 bits per second. After that, so first frequency, known tuning fork is loaded. After loading, we know that frequency decreases. Again, both these two are sounded together, then bit frequency, what happens here? Increase dimension. Calculate unknown frequency. The bit frequency, that is bit frequency, F is equal to FA plus or minus FB. Okay, plus or minus FB. We can take two cases, both cases we can take FA minus FB, and F is equal to FB minus FA. We don't know which one is greater. According to this equation, FA is greater. According to this equation, FB is greater. Out of these two equations, we know that already we derived in theory, bit frequency is equal to difference between two frequencies. The difference between these two frequencies less than 10 only. It is very, very small difference. Okay. FA minus FB or FB minus FA. Which one is greater? Here 256 they given. Either this one 256 plus 4, 260, or 256 minus 4, 252. We don't know that one. So then which equation you have to use? First equation you have to use or second equation you have to use? Question will be there here. Which equation you have to use? Okay. According to this loading, bit frequency should increase. Bit frequency should increase. Correct? Increase. See, arrow mark, increase arrow mark, marked over here. Now here, after loading of tuning fork A, frequency of this one, according to this frequency, what happens here? Decreases. Frequency of A decreases. Frequency of A decreases. Frequency of A decreases. Okay. It is goes on decreasing, decreasing, decreasing. It is not changing, it is decreasing. If it is decreasing, difference between these two, difference between these two, for example, I'll take here, see, first 100 minus 90, how much it is? 10. 100, after I'll take 98 minus 90, what it is? 8. 95 minus 90, what it is? 5. This frequency, what is happening here? Decreasing. But what is required? Increase. We required increase. That's why first one is wrong. Okay, similarly I'll take this one, correct? Now FB, for example, 100, this is greater, this one value you have to take greater, this is so less than that one, for example 90, it is 90. This 100, after loading, this frequency decreasing, this equal to 10, it is what? 89, what you got? 11. Now 100 minus 88, 12. See, this value, what is happening here? Increasing. So what is required here? Bit frequency should increase. Here bit frequency increasing. That's why we have to use this equation. So therefore bit frequency is equal to FB minus FA. Bit frequency how much here? 4. FB is what? Unknown, minus FA 256. Now we are going to find FB. FB is equal to 256 plus 4. FB is equal to what? 260. 260. Yes, one more numerical I'll solve. Just the concept to remember here. Just remember these two. It is enough. Remember this one. Loading frequency decreases. Filing frequency increases. Now, here two tuning forks are there. A, B. When sounded together, bit frequency, how much you got here? 6. Initially, before loading. And this is 512. And this one is unknown. We don't know. We are loading. Which one we are loading now? Unknown frequency we are loading. In this case, we know that two cases, F is equal to FA minus FB, and F is equal to FB minus FA. We don't know which one is greater. After loading, okay, one more they should give. Before loading, bit frequency is what? 6. After loading, bit frequency decreased, they mentioned. Decreased. After loading, bit frequency may increase or decrease. Here bit frequency decreased. It means that arrow mark is down. Arrow mark is down. Bit frequency decreased. Here tuning fork B, you are loading. If you are loading, frequency of tuning fork, what happens? Decreases. This decreased. This decreased. Okay, now this goes on decreases. This is constant, it is. If this goes on decreases, difference between these two, what will happens? Increases. Difference between these two increases. What is required? Difference should decrease. This is wrong. Correct? Okay, once again I'll say 100 minus 90. How much it is? 10. 100 minus 85. It is decreasing. This one decreasing. How much it is? 15. Difference is increasing. Here difference should decrease. That's why we should not use this equation. Now this is decreasing. What about difference? Also decreases. It is correct. See, for example, it is 100 minus 90. It is 95. It is 10. 90. It is constant. It is 5. Now 94 minus 90. It is decreasing. 94 minus 94. 92 minus 92. Yes, see, this decreasing. This equation is correct. Now F is equal to, what you can write? FB minus FA. Bit frequency how much? 6. FB is how much here? Don't know. FA 512. FB is equal to 6 plus 512. It is 6 plus 512. This is 518. This frequency of tuning fork V is 518. 518. Now one more case I'll say here. Frequency of B is 200. Before filing case I am explaining. Before bit frequency is 4 bits per second before filing. When it is filed, when it is filed, bit frequency increase they mention. How much increase they not mention? Increased. Calculate the frequency of A. Frequency of A. We know that two cases. One is F is equal to FA minus FB. Another one is F is equal to FB minus FA. Here bit frequency, what is happening? Increasing. Yes, but first you put arrow mark in upward direction. FB, in which tuning fork you are filing, to which tuning fork you are filing, that is tuning fork A. After filing, frequency, what I said, increases or decreases? Frequency increases. This frequency increased. This frequency increased. Okay. If it is increasing, difference all happens increase. This will not change. 100 minus 90, 10. 110 minus 90, 20. Yes. What is required? What we need here? This bit frequency should increase. That's why this is correct. Now we can see this one. If FA is increasing, difference between these two goes on decreases. That's why we should not use this equation. Now bit frequency, what they given? 4. Next, this FA, don't know. It is 200. FA is equal to 204. Like this. We can calculate. Here two tuning forks are there. FA is 212. FP we don't know. Before waxing, bit frequency is 6. After waxing, bit frequency 6 only. Which one you are waxing? A is A, B. This one loading or waxing, same. You are loaded with tuning fork A. Before loading, bit frequency is how much? 6. After loading also, bit frequency 6. In previous case we discussed there is a change in bit frequency after loading, before loading. But in this case, bit frequency, there is no change in bit frequency dimension. How to solve? Which equation you have to use? F is equal to FA minus FB. F is equal to FB minus FA. Which equation you have to use? Here bit frequency arrow mark we can't put, no. Why? Because there is no change. If it is increased, we can so mark over here upward direction like previous numericals. In this case, there is no change in bit frequency. Same. Which equation you have to use? Which equation you have to use? We can put a arrow mark for FA. Why? Because after loading, frequency of this tuning fork decreases. Frequency of tuning fork decreases. Okay, fine. This one decreases. Just one example I'll say here. This is 100 minus 90. Now 95 minus 90. This is equal to what? 10. This is equal to 5. Now 90 minus 90. What? 0. Now it is decreasing. 85 minus 90. How much? Minus 5. 80 minus 90. How much? Minus 10. Okay, fine. I'll say this one. FB is 100 minus 90. It is what? 10. 100 minus, which one changing here? FA changing. decreasing, that to decreasing, 20, 100 minus 70, 30, 100 minus 60, 40. Here bit frequency, what is happening here? Bit frequency goes on increases. Initially 10, before, for example, before loading at 10, after loading also again somewhere that should come 10. Why? Because see, before 6, after also 6 should come. See here, I'll take this one as a 94 and this is 84. 94 96, I'll take this one, 96. 96 minus 90, it is 6. 94 minus 90, it is 6. Okay. In this case, we got this value 2 times. We can see that this is before also it is 6 we got, after also it is 6 got. We can say that this same value will get 2 times. Here also same, after and before we should get same value. But in this case, we will never get same value. That's why we should not use this equation. For example, 10. Before waxing 10 is it 10. After waxing, again that should come a 10 over here. But here 10 will not come. Here before waxing 10 is there here 10. After waxing or loading, frequency goes on decreases. So somewhere again this value will come over here. It means that which equation is correct? This equation is correct. Now f is equal to f is what here? We can use this equation. F is equal to fa minus fb. We have to use f is 6, fa is 212 minus fb is unknown. FB you take LHS, 212 minus 6. That FB is equal to 212 minus 6 is what? That is 206 Hertz. Like this we can calculate. Yes, which negative sign? Someone asked question, which negative sign? FA minus FB, this negative sign, this negative sign. If this negative sign already in bit okay, here bit phenomena, here 2 waves are there. 2 waves will superimpose. After superimpose, 1 wave will come here. That 1 wave. For example, y1, the displacement equation for first one, y1 is equal to a sine omega 1 t. Y2 is equal to a sine omega 2 t. Omega 2 t. Okay. Omega 1, omega 2 have taken. Why? Because omega 1 frequency of first wave, omega 2 frequency of second wave. After superimpose, y is equal to y1 plus y2. After simplifying, you'll get waxing and waning. So just theoretical, I'll say here diagrammatically. Here 1 wave. Here 1 wave. And there is a slight difference is there, frequency difference is there between first wave and second wave. Slide. Like this. See, slide frequencies, slide changes there. Here crust and trough overlapping. Correct? Crust and trough. Here which one is overlapping? One is crust is overlapping with another trough. You'll get maxima or minima. Maxima will get maxima. Here maxima we got here. Maxima. Here not exactly overlapping. Little bit less will get. Here what is happening here? So 0 1 by 2. Next here, so it is a 0, complete 0. Again it is what? Okay. Here see, like this will come. Like this will come. Here again maxima will come. Again maxima will come like this. Here 1 wave is formed. That wave is called a bit wave. It is bit wave. If you simplify this one, we'll get bit frequency. It means that frequency difference between first wave and second wave. That frequency difference between first wave and second wave, f is equal to f1 minus f2 will come. This negative sign, the frequency difference between first wave and second wave will get a bit frequency. This negative sign. So if you simplify this one, you'll get one derivation is that derivation is not necessary. If you look in if you saw in that reference book, you'll come to know how they derived. You final that derived in bit phenomena, frequency is equal to f1 minus f2. F1 is the frequency of first wave, f2 is the frequency of second wave, and f is that is frequency of bit wave. After superimposition, whatever wave will form, the frequency of that one is f here. Condition for bits is the two waves should have slightly different frequency. One, for example, one is 200, another should be plus or minus 10, or it may be 210 or 190. That should not be this much different. It is 1, it is 100. It should not be like this. The difference between two frequencies should be less than 10. After subtracting these two, we should get less than 10. Then only bits will form. Okay. Yes, thank you.